Okay, continue with moment check. Now we check choice B. Choice B. We already have moment at this section, and MBC is assumed as redundant. And now we have to calculate MBA. So we can use this choice. Okay, choice B. In choice B, we have BC equal to 28.4, and here's MBC. And MBA now equal to MPC, then plus 28.4. Very simple, right? And similarly, at choice G, we already have a moment here, and moment here is MP, right? And in the previous step, we determine MGE, and now we determine MGH. Okay, MGH is function of MGE, and MGE is function of MBC. And here is MP. And finally, we have MG8 equal to the function of MBE. Here's M, not B, okay? MBE, MBC. Here's MBC and minus this one. Okay, so we can determine all of the moment at every section, right? Now we have moment here is 171.3. MBC is redundant. Here is 28.4. At this section, we have BA equal to MBC plus 28.4. And moment of this column, M is GE equal to this one. And this column, this section, okay? This section, moment equal to this one, okay? All of moment of all of section has been calculated, okay? But is this okay now? Not yet, okay? We have to check one more. This already checked, this already checked, but this one, 1, 2, 3, and 4 is not checked, and it should be smaller than MP. Okay, 1 and 2 and 3, 4 should be smaller than MP. So now we have to check this one should be greater than minus 100 MP and minus 100 and smaller than 200, minus 200 and 200. Okay, what else? This one, sorry, this one. Okay, this one here, this one greater than minus 200 and smaller than 200. This is MP. Okay, and what else? This one, moment at this section also should be within of MP, minus MP and MP, and this one also in the range of MP. Okay, so we have 1, 2, 3, and 4 equation. The first equation becomes same. The second equation becomes MPC, MBC in the range of minus 114.5 and smaller than this one. And this, the third equation becomes MBC greater than this one and smaller than this one. And the last equation becomes MPC greater than this one and this one. And so, what is conclusion? MBC should be greater than the biggest one and smaller than the smallest one. Okay, here MBC as a result of 4 equations. Okay, MBC should be greater than 85.5 and smaller than 171.6. Okay, what does it mean? What is conclusion now? In the previous class, I have already mentioned that if MBC has a range, then our solution is correct solution. Okay, again, in the previous class, I already mentioned if MBC has a range, so here has a range, then our solution is correct solution. Okay, and it's okay. Moment check is complete. Okay, moment check is complete, and lambda equal to this one is exact solution. Okay, exact solution. And now the moment diagram is this. Okay, moment diagram is this. And the second, noted that I have also already mentioned that in the plastic analysis, okay, in the plastic analysis, it is not required to have exact solution all of the section. Okay, it's don't need to determine the moment of all section. It's no need. It's not necessary because as long as the moment check show that every section, moment of every section is satisfied with moment check, mean moment at every section should be smaller than MP. That is enough, okay, for plastic analysis. Okay, for plastic analysis, moment of a section smaller than MP is enough. It's not need to calculate the unique value of moment at every section. Okay, so it means this moment diagram is enough for our further step if need. Okay, if need. So this is solution, final solution. Okay. Okay, and now we are going to one more example, one more applications of combined mechanism. Now we consider a bottle frame again with distributed load. Okay, distributed load. Here we have a bottle frame. Here the length of the dimension, the length of the beam is 20 feet, and the head, the column is 10 feet. The load here on the beam is distributed load 1.6 kg per feet. Okay, and the load at this point is horizontal load 24 kgs. Okay, 24 kgs. Now we have to determine MP, required MP, and MP it means it is a design problem. Okay, design problem. Determine MP. If we have MP, then we can determine the section of the section. Okay, dimension of the section. And if we consider also the action force, effect of action force and shear force, and we can calculate. But in this case, we just determine MP is enough. Then, if we have MP, then it is lower bound solution. To start with this problem, first we have to calculate n. N equal to n minus r. What is n? Upper n. 5. Okay, critical section for where the hinge might be formed. 1 and 2, 3 and 4 and 5. 1, 2, 3, 4, 5, maybe. R equal to 3. Okay, the number of redundancies or the degree of redundance. r equal to 3 and n equal to 2. With this frame, we already know. Okay, it means we have two independent mechanism. Okay, two independent mechanism. Which one? The first is strain mechanism, okay, or panel mechanism. Panel mechanism, and the second with okay, with strain mechanism or panel mechanism, we have external work equal to 4 MP, 1, 2, 3, 4, and the external work. We have load here, okay, 24, and multiply by this equal to this, and MP equal to 60. For beam mechanism, okay, here is beam mechanism. Then, how to determine the internal and external work? For internal work, we have 1 and 2 and 3 and 4 MP, okay, 4 MP. How about external work? Please note that here is distributed load, okay, distributed load. Okay, distributed load. And this load is 1.6 kg per feet, okay. Then the length is 20. So the load, the total load equal to this one, 1.6 multiplied by 20 feet. 20 feet, it is length, and divide by 2. Okay, divide by 2. This is the load, the total load, multiplied by this distance is 10 theta. Okay, so for distributed load, in the textbook, they already introduce this equation for distributed load. Okay, one for the distributed load multiplied by the length of the element and divide by 2 and multiply by the deflection, maximum deflection here. And finally we have this one. And from that we have MP equal to 40, corresponding to beam mechanism. Okay, so here we have two independent mechanisms, including panel mechanism and beam mechanism. And now we combine beam mechanism and panel mechanism together. Combined mechanism. This is combined mechanism. Okay, moment here, plastic hinge maybe here and here and here, but note that in the beam we have not know where is the plastic hinge might occur. We don't know where, maybe in the middle or maybe in somewhere, so we just assume the location of plastic hinge is here. The distance from here to here is g. Then the remaining length is 20 minus g. Okay, so we assume. And if we assume this angle is theta, then this distance is z multiplied by theta. This angle is 20 minus divided by 20 minus g theta. Okay. And what else? This angle is g for the beam. Z divided by 20 minus z theta. For the column is theta. Then the whole angle here is 20 divided by 20 minus z theta. Okay, this one plus this one. So here theta, then here is this one, and this distance is g theta, and this rotation is this. Okay, then based on that we can develop the equation of work or work equation. It is internal work. Okay, MP multiplied by 2 theta here and here, and multiply by 2 times of this one and this one. Okay, equal to this one due to the horizontal external force. 24 multiplied by 10, it is 10 theta. And this part is due to the vertical. Okay, vertical. This distributed load, this part is due to distributed load, and z theta is here, z theta. Okay, then z theta here. Okay, then we have MP. MP as a function of z. Okay, MP as a function of z. MP as a function of z. How to determine MP and z? As you know that MP should be the maximum value among the moment in the beam. And now it's easy to determine the maximum value of MP. You can take a derivative of MP over z equal to 0. Okay, equal to 0. It means take a derivative of this equation equal to 0. Then we determine z. Okay, and z equal to this one, 6.83 feet. Okay, do you understand this step? Can you follow? Okay, to determine the maximum of this value, we take the derivative of this function equal to 0, and by that we can determine z equal to this one. Okay, then now we have z, then just replace z, substitute z into here. Okay, then we can determine MP. And MP, the exact solution, MP equal to 69.34 gives fit. Okay, gives fit. This is exact solution of MP. Okay, as a result of combined mechanism. Okay. This is, remember, this is exact solution 69.34 give fit. It is solution. Okay, and now because z equal to 6.83 and m equal to 69.34. Okay, so now we try with approximate analysis for distributed load. Approximate analysis. Okay, what is approximate? Approximate. We can assume plastic hinge location. This is exact solution, exact location of the hinge, but we can assume. Okay, we can assume the plastic hinge at 1/3 of the beam here. Okay, so let's say z equal to 20 divided by 3 equal to maybe 6.666 something, nearly 6.667. With this, we have MP equal to this equation. Okay, then with this assumption, the errors, location errors is 20%, 2%, only 2%. Okay, very small, because here is 6.83 and this is equal to maybe 6.667 something. So the error may be 2%. Then replace this, substitute z into this equation, and we have MP equal to 68.6. The error may be 1%. Okay, compared to the exact solution. Okay, 1%. Now we can assume another assumption. Z the location of the hinge at the middle of the beam. Is it okay? So it means Z equal to 10. And this place 10 to here. With this one, the location errors is 50%. Okay, 50%. The exact solution is here, but it is assumption. Then MP equal to 66.67. The error just 4%. Okay, 4%. So 4% is very small. And what else? If we assume 2/2 of the length of the beam at this point, so equal to maybe 2 times of this one. Okay, then the MP equal to 48. 48. What is conclusion? The conclusion is we assume with the considerable errors in the plastic hinge location, but it makes just a little bit error in MP. Okay, so we can calculate the errors here. So of course we have never assumed this one. Okay, just assume at the middle or somewhere. But even though the error of the location assumption is 50%, okay, but the error is very small, just 4%. In practical analysis and design, this error within maybe 10% or 5%, this error is acceptable. Okay, acceptable. It is very small errors. Okay, so in this case, although the location of assumption of the location is not correct, okay, very far from the exact location, okay, far, but the solution is acceptable. Okay, so in this case, our assumption is not have much effect on the final result of the solution of MP. Okay, that is conclusion. Compare with the correct solution. Okay, and we show that not much errors. Okay, so that is a conclusion. Okay, so until now, many application of work method has been introduced and explained. We have we had independent mechanism or and combined mechanism. Okay, we should start with independent mechanism, and to start with independent mechanism, we have to determine the number of independent mechanism. Okay, and you have to remember the equation to determine the number of independent mechanism, and then combine one by one. Okay, one by one, and then we have full combined mechanism, and beyond that we can determine the solution. And then we do the moment check. To do the moment check, we have to calculate the number of independent redundants. Okay, beyond the number of redundants, we have assumed the redundants and calculate the remain unknown as a function of redundant. Okay, then we do the moment check. If the assumed redundant has a range, then our solution is correct. Okay. Okay, so homework is problem 5.4 in your textbook. Okay, do the homework. Okay, thank you and see you again. Bye bye.